Orbital box diagrams will take the specification of the electron's locations one step further beyond your regular configurations. And instead of just showing the number of electrons per sublevel, which is really useful, we now actually can see the number of electrons per orbital, which, if you saw the very first video, sort of represented them as boxes. And these are the three-dimensional regions in space where the electrons are usually found. So the orbital box diagram is going to have to represent each electron, and we're going to do that in the form of an arrow pointing up and an arrow pointing down. That would represent 2 electrons inside one orbital. There's a few rules to keep in mind. The alpha principle that was presented in a previous video is still valid, and that's the idea that we start at the lowest sublevels and we work our way up. The next one to keep in mind is Hund's rule. Hund's rule, if you want to think of bus seats, sometimes people call it the bus seat rule. It's the idea that when you get on a bus with strangers, you don't automatically go and sit next to a person. You try and spread out and find an empty seat. And then when you have to, suppose it's crowded, that's when you sit down in a spot near somebody. So the electrons do the same sort of thing. They tend to spread out within a sublevel. So within like the 3D sublevel where there's 5 orbitals, you will need to have spread out 5 electrons, one among each of those orbitals, before you start doubling up. When you do double up, you will have to make sure that one points upward, one of those arrows, and the other points downward. This is going to help satisfy another rule that you need to know, and that rule is called the Pauli exclusion principle. And the Pauli exclusion principle is the idea that no 2 electrons can have the exact same 4 quantum numbers. And there's a whole separate video and a guided note sheet about quantum numbers. But the idea here is if your 2 electrons are in the same principal energy level, the same sublevel, and the same orbital, that's 3 of the quantum numbers, and they're all going to match. Now, if you point them in the same direction, like both spinning up, that's their 4th quantum number, and it would also be the same. And then there's no way of distinguishing between those 2 electrons. So if they're in the same orbital, one has to point up, the other points down. And the common notation is to put the up-spinning ones first. So let's look at a couple of examples on the next page. Suppose we want to look at nitrogen. Nitrogen has 7 electrons. So if we were to write out its configuration, we would have said 1s2, 2s2, 2p3. And because I typed it, the formatting is a little bit off. When you draw this as an orbital box diagram, what you really can do is you would label one section as 1s, and you have 1 electron spinning up, 1 electron spinning down. My arrows, in this case, you see they have half of a head on them. You can certainly draw them normally with a fully pointed head. In level 2s, it contains only 1 orbital as well. So we point 1 up and 1 down. And then when we get to 2p, there's 3 orbitals, and I need to show all 3 of them, even if some of them are empty. Because if you don't show me the blank empties, I don't know that you really understand how the diagrams work and how many orbitals are present. So in this case, I'm at my 2p sublevel, and I really should label all of these. So 1s over here, 2s. And then when you get to the p's, sometimes you might see them labeled 2px, 2py, 2pz to indicate the axes in space in which these orbitals are oriented. I don't generally label it that way, but it's not unheard of. And then among those 3, since their energy is identical, my electrons, my 3 remaining electrons want to spread out. So I'm going to have 3 orbitals here that have unpaired electrons. There's a single electron in each of them. There's not a single set of pairs in the 2p sublevel. If I look at something like, let's try something like scandium. The first thing you're going to want to find out is how many electrons it has. So go to your reference table and look that up. And you'll find that its atomic number is 21, so there's 21 electrons. So we start with 1s. We label it. I can draw this as a line or a box. It doesn't matter which. I typically draw lines. And we do one up and one down. And then there's sublevel 2s, which because it's s only has one orbital. And I can put 2 electrons in it, so one up, one down. When I get to 2p, I'm going to fill this with 6 electrons. And to set a good habit, instead of just doing up, down, up, down, up, down, it really is in your best interest to spread out first and then come back and double up, pointing down. It doesn't generally matter in which box you start those down arrows, whether you work from left to right or right to left. I think out of convenience and just tradition, most people go from left to right. But among those 3 orbitals, there is no difference in their energy. So you would not have an excited electron if your first electron had gone into the second or the third orbital before it did the first. After 2p comes 3s. So we'll put in our 2 electrons, one up and one down. And at this point, we have a total of 2, 4, 6, 8, 10, 12 electrons. We have 9 more to go. So after 3s comes 3p. And again, just like the 2p, it's best off to represent them with up, 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 and then down, down, down. After 3p, it does not come 3d. The next one is 4s, which has 1 orbital. So this will take 2 of my remaining 3 electrons. And then I finally have 3d. And if you recall, the d sublevel has 5 orbitals. That's where the maximum of 10 comes from. So make sure you do draw all 5 boxes, or all 5 lines. And then scandium only has 1 more electron, so I'm going to put 1 up electron in my first available orbital.